Today, we're going to continue our discussion about probability distributions by talking about the binomial probability distribution. The binomial probability distribution will be looking to find probabilities. Surprise, surprise, right? We'll also be learning about how we can find the mean and standard deviation of the binomial distribution and how we can interpret results that we get and tell if they're significantly low or significantly high. So first things first, what even is the binomial probability distribution? Well, there's 4 requirements for a probability distribution to be a binomial probability distribution. The first, there have to be a fixed number of trials. So trials are single observations, and we have to ahead of time say, I'm going to do this many of them. Okay? So the second requirement is that the trials must be independent. So the outcome of any one trial doesn't affect the probability of the other trials. The third requirement is that each trial must have 2 possible outcomes. And it might be that there's lots of outcomes, but we're going to be classifying them into exactly 2 categories, and we have to be able to do that. That's probably the biggest key between a binomial probability distribution and some other options for probability distributions. So 2, binomial 2, all right? 2 categories. We normally call them successes and failures, and we'll be following that throughout this lesson, all right? So the fourth and final requirement is that the probability of a success remains the same for all trials. So it can't be changing as we move through the trials. So as always, we've got some notation that's going to go with this stuff. So the notation for binomial distributions, we're going to use a capital S and a capital F for success and failure, right? We'll use the capital P for probability, so the probability with S in parentheses, probability of S is going to be a lowercase p. So whenever we see a lowercase p with binomial probability distributions, we'll think that's the probability of success. The probability of a failure is going to be 1 minus p, which we're going to define to be a lowercase q. So whenever we see a lowercase q with binomial probability distributions, we'll be thinking probability of a failure. And finally, we'll be using n for the fixed number of trials. Hopefully you're saying, wait a minute, that's not enough, because we were talking about having these successes and failures. How many of them do we have? So x is going to be the specified number of successes in n trials. So x can be any whole number between 0 and n, right? And again, p is the probability of success in one of the n trials. Q is the probability of failure in one of those n trials. And p of x is going to be the probability of getting exactly x successes among the n trials. Right? So really quick, an important thing. A lot of times when we use the word success here, you should be cringing a little bit because successes are not always good things. Sometimes we'll be looking at the success that we find this many people with cancer, or we'll be looking at the success that this many deaths occur. So success is sometimes really not a good thing. So when we use that, realize that what we're doing is we're using the word success more in like the success that we found what we were looking for. And what we were looking for may or may not be a good thing. So success is arbitrarily used, and don't always think that the good thing has to be the success. The success is more whatever we're looking for. So it's really important that whichever of the options we define as success, the probability that goes with it is p. All right. It depends on the way you look at it, on which of the 2 categories you might define as success. So that matching of when you're looking for x successes and p is the probability of a success, those need to be referring to the same outcome. So it's a good idea to get in the practice of writing down what is a success, since it doesn't necessarily correspond with what your brain will naturally think feels more successful. So let's take a look at an example. Right? When an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is, based on results from a Pew Research Center survey. So suppose that we want to find the probability that exactly 3 of 5 randomly selected adults knows what Twitter is. All right, first thing we want to know is this a binomial distribution? And if it is, let's figure out what these values for n, x, p, and q are. So taking a look at this and thinking about the 4 requirements that we have, well, the first one was that we had to have a fixed number of trials. We had to have a determined number of trials. Well, we were told that we were going to choose 5 adults, so we have 5 trials. The second requirement was that the trials are independent of one another. And in this case, they are, because the probability that an adult knows about Twitter is not affected by the results of another adult that was selected knowing about Twitter. Our third requirement was that each of the trials had to have 2 possible categories of outcomes, and we have that here. Either they know about Twitter or they do not know about Twitter. And finally, for each randomly selected adult, we had to have the same probability for each of our trials, right? So 0.85 being the probability that that person knows about Twitter, that's the fixed probability for each of our trials. So that means we can move on to B and we can figure out the values of these variables n, x, p, and q. So since we're selecting 5 random adults, we're randomly selecting 5 adults, n is going to be 5, that's our number of trials. And since we're interested in knowing the probability that exactly 3 of them know about Twitter, x is going to be 3, and in doing so, in choosing x equals 3, we've now said that a success is going to be defined to be knowing about Twitter. So since we now know that the probability of success corresponds to the probability of knowing about Twitter, then our probability of success, or lowercase p, is going to be 0.85. And the probability of failure is going to be 1 minus p, which is 0.15. So q, the probability of a failure, will be 0.15. Right? Again, make sure that x and p are talking about the same thing, that they're both referring to whatever you have decided is going to be a success, and make that note if you need to do so. Also, we talked about this earlier. If we have a sample of 5% or less of the population, even if the outcomes are actually dependent, then we can treat them as independent because the sample is such a small proportion of the population. Now that we know what the binomial probability distribution is, we probably want to be able to find these probabilities. So we've got a few methods, few options here. We're really going to focus on 2 of them, and ultimately really focus on this one, method 1, having the binomial probability formula. This formula looks like a lot, but again, I really want you to know how to figure it out. I don't really care so much that you memorize the formula. There's actually even a typo in this formula in the way it is here. So the formula should read that the probability of x equals n factorial divided by the quantity n minus x, not x minus n, factorial times x factorial times p to the x times q to the n minus x, and x should be able to be any value between 0 and n. Now remember, x is the number of successes among n trials, p is the probability of success, q is the probability of failure, and n is our number of trials. So let's use this formula, go through an example, And then at the end of this video, we'll take a look at this formula and break it down a little bit more. All right, so first things first, an example. Going back to our Twitter example. We already identified that n equals 5, x equals 3, p equals 0.85, and q equals 0.15. Well, if I wanted to find the probability that exactly 3 adults knew about Twitter, then I can use this formula. So I'm really looking for the probability of exactly 3, or that x is 3. So filling in these values to the formula, I find that the probability of 3 successes equals 5 factorial divided by the quantity 5 minus 3 factorial times 3 factorial times 0.85 raised to the third power times 0.15 raised to the 5 minus 2 power. So working through all of that arithmetic and finally rounding down to 3 significant digits, I'm going to find that the probability that exactly 3 of the adults know about Twitter is 0.138. Now let's take a look at a second method. All right. Another method that we have as a possibility is to use technology. All right. There are tons of different statistics technologies out there, and many of you will use various ones for different reasons as parts of various courses. So we're really just going to focus on, if we had technology give us something, how might we be able to use it? All right. So we're going to notice that in each of the displays, we're still going to be looking at this n equals 5, the probability of success is 0.85 deal. So in each of the displays, the probability distribution, it's given as a table. So we have the option of StatDisk. It prints out the table, and we have TI-83s and 84s can give you a table. Excel can give you a table. Minitab can give you a table. And notice if we take a look at the row in each of these where x is 3, we see the probability of 0.138 that we found using the formula before. All right, so that's about as far as we're going to go with the technology thing. And we are going to do an example really quick to practice looking at the StatDisk deal a little bit closer because it's so small here. So the overtime rule in football, we've looked at this example before. So there's 460 NFL games that have gone to overtime in the last, between 1974 and 2011. And 252 of them were won by the team that won the overtime coin toss. So we want to know, is 252 wins in the 460 games, could it be random chance, or is it more likely significantly high or significantly low? All right, so we're going to answer this question using binomial probability distribution. So if it's just random chance, then the probability of success should be about 0.5 and the probability of failure should be about 0.5. They should be equal. All right, so we have n is going to be 460 trials. Probability of success is 0.5, which is equal also to the probability of failure. And since we want to know about 252 games, we're going to choose x being 252. That's our number of successes. And we could use technology to help us out. We could use the formula. We could use a table, except tables don't go up to n equals 460. When you get to the larger numbers, they tend to jump more, and 460 is not included. The formula gets really, really kind of nasty and might shut some calculators down with the size of the numbers involved here. So what we're left with then is to use technology to help us out. So using StatDisk, we end up with finding that the probability of 252 or more wins in 460 overtime games is 0.0224. And we've rounded it to the 3 significant digits there. So this is less than 0.05. So what this is telling us is that the probability of this happening by chance, 252 wins out of 460, is not very likely. And in fact, it is significantly high. All right. So in the stat disk output, you can see the blue row highlighted there is 252 for X. That's where we are interested in. And the column that we're looking for is the probability that we are at X or greater, because we want to know about 252 or more games. So we're going to that column, which happens to be the far right column there. And that value is 0.0224 if we round it, which is what we found before, and what we presented here. So we can use technology to help us out and find these things. And again, doesn't look like it's chance. And so what this is telling us is when a team wins the overtime coin toss, they are in fact more likely to win the game. They have a better chance of winning the game. All right, our third method is going to be using a table. All right, so there's a table in your book. Any stats book should have a table of binomial probability distributions in it. The internet also has them all over it, and they should all look basically the same. What these tables are is printouts of what technology would give you. And so to use the tables, we need to know values of n and p, and that's going to give us the table that we're going to use. And then we're going to look at our value x in the table, and it'll give us our probability. Right. So let's take a look at an example. So based on a Harris poll, 60% of adults believe in the devil. Assuming that we randomly select 5 adults, we're going to use the table to find the following. So the first one is the probability that exactly 3 of the 5 adults believe in the devil. And the second one is the probability that the number of adults who believe in the devil is at least 2. So here's the way the table ends up looking. So we go through, we select n equals 5, we go over to our column of our probability that we're interested in, and we end up with this information that's given in the table on the right. So we have x values between 0 and 5, and we have probabilities given for each of those. All right, so if we're looking in our probability is 0.6 column with our n is 5 table, we're going to end up seeing that the probability of 3, we can read that out again in that table on the right. We're looking at the row that has x is 3 and gives us the probability of 3 is 0.346. So if we take 5 randomly selected adults, the probability that 3 of them believe in the devil is 0.346. Now, if we want to find the probability that at least 2 adults do, we're going to be looking for the probability that exactly 2 do, exactly 3, exactly 4, or exactly 5. Okay, so we find this by taking the probability of 2 plus the probability of 3, plus the probability of 4, plus the probability of 5. And we can go to the table that we had and add together the probability of 2, 3, 4, and 5. We're looking at those last 4 rows of our table, adding all of those together to get a probability of 0.913. So again, that's the probability that at least 2 adults of our 5 randomly selected ones believe in the devil. All right, finding the mean and the standard deviation. So when we have binomial distributions, it's really simple to find the mean, actually. We're going to take the number of trials we have and multiply it times the probability of success. That's the mean. To find the variance, we're going to multiply the number of trials times the probability of success times the probability of failure. And as it always has been, to find the standard deviation, we'll take the square root of the variance. So the square root of the number of trials times the probability of success times the probability of failure. We also still have our range rule of thumb that we can use to determine if outcomes are significantly low or significantly high. So values less than the mean minus 2 standard deviations will be significantly low. Ones higher than the mean plus 2 standard deviations will be significantly high. And everything in between will be values that are not significant. So let's go back to the football thing and figure out, well, is the result of 252 overtime wins significantly high? So to do this, we need to find the mean and the standard deviation for the number of wins in groups of 460 games when we have our probability of success being 0.5. And we'll need to use that range rule of thumb. So first things first, let's find the mean and the standard deviation. The mean we find by taking n, our 460 games, and multiplying times 0.5, the probability of success. So the mean is 230.0 games. The standard deviation we find by taking the square root of our variance. And we find our variance by taking n times p times q. So we'll be taking 460 times 0.5 times 0.5 and taking the square root of it. So we'll be getting 10.7 games as our standard deviation. So for random groups of 460 overtime games, the mean number of wins is 230 games, and the standard deviation is 10.7 games. So now we can use our range rule of thumb. So our range rule of thumb says take the mean, subtract 2 standard deviations. So I do that, I do 230 minus 2 times 10.7, and I get 208.6 games. Similarly, the range rule of thumb says take the mean, add 2 standard deviations. Doing that, I get 230 plus 2 times 10.7, which is 251.4. So now the range rule of thumb tells me that significantly low numbers of wins are going to be 208.6 games or fewer. Significantly high numbers of wins will be 251.4 games or greater. And the values that are not significant are the ones between 208.6 games and 251.4 games. So this gives me the outcome that the result of 252 wins is in fact significantly high because it's greater than 251.4 games. And our idea of when we say things are significantly high or significantly low has not changed. We're looking for that probability of 0.05 or less that this happened by chance. Okay, so now let's go back to that formula and break it down, because the formula is incredibly important for you to understand, except you don't have to know the formula. I want you to know what is this formula doing and be able to do what it's doing, whether you write it the way that it looks here or not. In fact, I really hope you don't write it the way it looks here because there's a typo in it. It should say n minus x factorial in the denominator. It should not say x minus n. So again, n minus x. So if you see n factorial divided by n minus x factorial times x factorial, this might look like the combination formula to you, and you would be 100% correct. That's what it is. So whether or not you are comfortable using the combination formula, you still don't have to be comfortable using it here. What goes in place of that chunk of variables is the number of ways to choose X outcomes from N trials. All we're doing is looking for the number of outcomes that have exactly X successes. So we're choosing the X successes from our N trials. And we're saying, how many ways can we do that? Right? We can't tell the difference between the successes. That's why we're in our combination deal instead of our permutation deal. So once we have the number of possible ways to choose X successes from N trials, then what we're doing is we're multiplying times P to the X times Q to the N minus X. This is multiplying the probability of success times itself for as many successes as we have, and the probability of failure times itself for as many failures as we have. So what each of this does, or what this does, is it tells us the probability of getting X successes among N trials. Right? So this is the probability of success and success and success, and success, so on until we've gotten to the number of successes, and the probability of failure, and the probability of failure, and the probability of failure, on until we've gotten all of our failures. So the multiplication rule says if I want to know the probability of the number of X successes, this is what I should do. All right, they were independent events, so I get to just multiply and not worry about anything else. So that's really telling me the probability of X successes among N trials for just one possible way of doing it. But there's more than one way to do it in most cases. And so I'll be adding that to itself over and over again because my addition rule says, hey, that order, or that order, that order, I've got the word or, I need to add my probabilities together. So I'm going to be adding them together to itself over and over again for as many possible orders as there are. And adding something to itself over and over again, it's just multiplying. So if I multiply by the number of possible orders for my successes and failures to come in, then I have my probability of X successes. And that's what this formula is doing. So don't let the formula intimidate you. Just remember what it's doing and be able to do that whether it looks like this or not.